Hello, everybody. Hello, NormConf. My name is Peter. And as was just mentioned, it's all about cost. This talk is about how to think about machine learning products, specifically from an engineering perspective, to try and save money. So first off, who am I and why am I talking to you today? Well, my name is Peter Sobot. I'm a staff machine learning engineer. By day, I work on audio-based machine learning for all sorts of interesting purposes, trying to tell people how happy songs are or how energetic songs are, and doing all sorts of cool stuff with data and music like that. If you've been online on Twitter and you do audio-based machine learning or anything to do with audio, you may have seen one of the packages that I work on called Pedalboard for doing nice stuff with audio in Python. But today, I'm not talking about any of those specifics or what I actually do day to day. Today, I'm focusing on how I tend to apply engineering principles to the world of data science and machine learning so that we can deploy things to millions and millions of users without breaking the bank. And I really want to focus on this word engineer first, because this is really where I'm coming from. I don't consider myself a data person or a data science person or anything like that. I've been working in machine learning for years now, and I have a good grounding in it. But when I really come from, my background is really more in what I would call traditional engineering. I was educated as an engineer, as a software engineer technically, but still at a school that really focused on things like engineering for bridges and engineering for roads and engineering for all these kind of big structures that humans have been building for hundreds of years. Now, how does this relate to data science and machine learning? Well, engineering is really all about building systems that are scalable, reliable, and come within cost and budget and things like that. And the reason it's kind of treated as a separate discipline, or it's something that people give a name to, is really that these systems fail over time. And over the past couple hundreds of years, many of these engineering systems have failed, and we've learned terrible lessons about that. The bridge you see on the screen here is not actually just any bridge, but it's a bridge called the Quebec Bridge in the Canadian province of Quebec. And it fell down twice during construction. And we have this bridge to thank, or specifically the negligence of its engineers, for what we call modern engineering today. So if you've ever heard of some engineers having licenses or being professionally regulated or being members of professional organizations, specifically outside of tech, this is very common. And that's because this bridge failure and the corners that were cut during this bridge's construction really started the process of having engineering being more regulated and being treated like a very serious profession in a way. Fun side note, if you're a Canadian engineer like I am, when you graduate, you get a ring from this bridge, or supposedly made from the iron of this bridge, to remind you every time that you sign your name to a document, the bridge fell down. Make sure you're doing this right. But I digress. This bridge really fell down because corners were cut and constraints for the problem were not well observed. Engineering fundamentally is about building the best thing that you can given the constraints of the problem itself. And many of these constraints are kind of obvious. So you got things like safety and reliability. You want anything you build to be safe and reliable. And others apply to really any project, not just engineering projects, like time and cost, right? We don't have infinite time to build a system. We don't have infinite budget to build a system either. So this brings me to the way that I think about engineering in general, and this applies to machine learning just as much as it applies to bridges. Anyone can build a bridge that stands, but it takes an engineer to build a bridge that barely stands. And this seems kind of flippant, and it is. But what this really means is it takes an engineer to build a bridge that is cheap enough so that it barely stands, right? It takes an engineer to build a bridge that meets the design criteria in such a way that it fulfills all of the things that we need to fulfill, right? It's not over budget. It doesn't take forever to build. And we can do it without bankrupting the town that asked for the bridge or the company that asked for the software to be built. In this case, think about the fact that the Romans built bridges thousands of years ago that still stand today, but they were extremely expensive even by their standards. And today we wouldn't do the same thing because we have cost to think about. So to finish off this little tangent about engineering and kind of where I'm coming from here, I want to compare two different fields of engineering. And that is civil engineering, where we're building bridges, and software engineering, where we're building, well, software. And that includes data systems and ML systems and whatnot. In both of these fields, one of the most important choices you get to make when you're starting a project is what material to use, or what tools, what frameworks, and so on to use. In civil engineering, this might be what you literally build your bridge out of. In software engineering, this might be what framework do you choose, or what language do you use, or things like that. And these all have different trade-offs and different costs and different amounts of performance you can get from them. In civil engineering, you might build your bridge out of wood, and that's great. It's plentiful. It literally grows on trees. Everybody knows where to get wood from. And in software engineering, the analog might be something like JavaScript. It runs everywhere. Seemingly everybody can write JavaScript. It's very, very common. It's cheap to build, but it might not be as powerful as you want it to be, or it might not be able to do certain things that you want your software to do. In civil engineering, you might use iron if you want to build a bridge that's a bit more sturdy than your wooden bridge there. And in software engineering, maybe we would choose Python. Again, a little bit more expensive, maybe sometimes harder to build, but gives us more performance. Continuing down the list, you might use steel to build your bridge if you really want something that is very performant or very sturdy. And in software engineering, maybe you want to rewrite your code in C++, if you want to make it even faster to run, or to run in certain scenarios where Python is just too heavy or too slow, but it takes a lot longer to write your code, so it's more expensive. And then continuing to the very bottom of the cost here, or I guess the most expensive options, in civil engineering, there are new materials that people are using all the time, one of which, for example, might be carbon fiber. You wouldn't build a whole bridge out of carbon fiber. That's quite expensive to do. But for certain applications, carbon fiber really gives you a lot of strength, and it can do things that other materials cannot do. And the equivalent here in software engineering, in my opinion, is machine learning. It's like the carbon fiber of bridges. You don't want to build an entire bridge out of carbon fiber. You wouldn't want to build your entire project out of machine learning, but it's got some very, very nice properties. And if you're willing to pay for it, it can do some things that other materials cannot. So if machine learning is the new expensive tool that everybody wants to use, then how can we use less of it in order to save money? How can we still get the benefits of machine learning, but not have to put it everywhere in our product and use it as minimally as possible to still make it economical to deploy? That's basically the entire point of my talk today. So let's dive into this. Congratulations. You and I, everybody on this call, we all now work at a new company. And this company is called Video Chat Inc. It's actually the video conferencing platform that we're using right now to host this conference, and it's how you might talk to your coworkers every day. This fictional company is the world's most popular video conference platform. And we are engineers or data scientists or machine learning people on one of its engineering teams. And we've been tasked with building interesting new features for video chat. One such new feature just came on our desks right now, and it showed up as this RFC. The business people and product people at Video Chat Inc. want us to build a coffee brand detector. Now, what that means is they want us to build a system such that on each video call, Video Chat Inc. can automatically detect the brand of coffee that shows up in video calls, and then automatically put a button on the screen so users can reorder their coffee and stay caffeinated without even leaving their seats. Sounds like a pretty lofty idea, but it also sounds like something that isn't impossible to build. So we might as well get started here. Now, if you're a machine learning practitioner, as soon as you see something like this, you might start to think of ways to implement it. You might jump in and say, well, I could use an object detection model. I could use PyTorch Vision or ResNets or any things that you've seen online or in the community. And that's great. But coming from an engineering perspective, that's like someone telling me to build a bridge and me saying, well, I'd love to build that bridge out of wood, even though I don't know which river it's going to cross or how many people need to be on top of it, right? We don't need to use our tools anywhere near this point in the process. We should instead figure out what this project needs and what the requirements are. So let's do that. Let's say that we've worked with the product team and the business team to figure out the actual needs here, and we've come up with a list that we can use to start building. This does sound kind of waterfall-y and less agile maybe, but for a big project like this, we need at least some guidelines to work within. So we've come up with these requirements, and I've split these requirements into two different lists. Now, they're in two different lists because this is a technique that comes from more traditional engineering. We've got one list called functional requirements and another called non-functional requirements. Now, the functional requirements are things that we need to make this system work in the first place, right? So this functional requirements list is how we judge if the system is done, if it's been built yet. And then non-functional requirements are ways that we can evaluate how well we did or the quality of the final system. So regardless of if it works, was it cheap enough for us to build, or is it fast enough if it's a software system, stuff like that. So our fictional system here is going to have a couple functional requirements. We need to be able to detect the top 10 most popular coffee brands that show up in people's video calls. We also want to be able to detect the brand of up to 1,000 users of the system per day. So that's our load. That's kind of our scope here. And then also our system must have a precision of at least 99% and a recall of at least 90%. So these numbers are kind of just picked out of thin air, but we can try to build a system that does have these numbers. And then for non-functional requirements, well, we want the system to cost less than $100 per day, which is quite a tight cost bound, but we definitely want to make sure that we respect that because that's going to determine if we can deploy this or not. And the system must provide data by the end of each day. So it doesn't really matter exactly how quickly or how slowly it works, as long as we give the results to the business about the end of each day. So with those requirements in mind, let's do some engineering. So big disclaimer first, the following calculations are incredibly oversimplified to make a friendly and digestible point in a 20-minute talk. Do not depend on these numbers. You might find bugs in them. You might find miscalculations. But given that, please continue to suspend your disbelief for the rest of my talk here. So following from Joel's talk that you just heard from, let's start with the simplest thing that might possibly work first. Let's have attempt number 1 at the bottom of the screen here. Let's just run machine learning on every single frame of the video we get in real time. So we get frames coming in from our customers, just like what you're seeing right now. Some of these frames have coffee cups in them and others don't. And let's say we pick an object detection model off of GitHub. Someone's already pre-trained one for us, and it has the required accuracy that we're looking for. Let's just run that on every single frame of video in real time and take the outputs and put them into some sort of aggregation tool for later. Now, I'm going to do a bunch of back of the envelope calculations here on the left-hand side, and I'm going to fill up with a bunch of numbers, but don't be too scared. I'll talk through every single number as we go through. We know our daily compute budget is $100, so that's what we want to be underneath here. And we know we get in 30 frames per second of video from each user. We also know that this PyTorch model we have here, well, let's say we've measured it and we found that there's a certain number of floating point operations we need to do in that model to process each frame. From our measurements, that turns out to be about 40 billion floating point operations, which sounds like a lot and kind of is a lot. But multiplying these numbers out tells us that we need about 1.2 teraflops per second of computing power to process these videos in real time and give us results. That's actually kind of doable on modern GPUs. This is not too out of the ordinary. Then we also know we have a maximum daily load of 1 million users. We know that we have about 4 hours of daily usage per user. People are on this app all the time because they use this to talk to their coworkers and they spend half their days in meetings, or at least I do. And then that multiplied out means that our daily hours of video is 4 million hours per day we need to process. So that's quite a bit of video. Then multiplying that by the number of teraflops per stream, well, that means we need 17.3 zettaflops or zettaflops. I don't know how to pronounce this number, but it's a lot. And we're going to have to use that to estimate our cost here. So let's say we have GPUs available in our cloud of choice, and we're using the cloud here. The flops available per GPU turns out to be 8.7 teraflops. And dividing those two numbers, we need 551,724 GPU hours per day to make this work. That sounds like a lot. But let's suspend our disbelief here and say that we can get that amount of GPU capacity, and we just have to pay for it. Looking at our price sheet here, let's say our cost per GPU hour is 45 cents. And that means our total daily compute cost is only $248,275 per day. That's $250,000 per day. I don't know about you, but that's not viable for any environment I've ever worked in. And if I presented that to the folks who asked for a product like this, they would probably laugh me out of the room and find an engineer who can build a system that actually works. So let's see which numbers that we can change here. What can we look at to make this system cheaper without sacrificing our functional requirements like our accuracy and our load and such like that? Well, to start with, we have the number of frames per second that we're processing here. We're processing every single frame of video right now. So attempt number 2 might be something as simple as just run the ML on fewer frames, right? Just run ML on some of the frames. Don't even change the model just yet. Let's just subsample the stream. And I know this is a big if. We don't actually know if this is going to work, but I'm going to guess that if you're drinking coffee, you can't raise the coffee cup to your mouth and take a drink in less than 1/30th of a second. It's going to take longer than that for you to actually take a sip of coffee. So this assumption might have to be tested offline, but let's run with it. This reduces our frames per second to 1 frame per second. And then our per stream compute is now 30 times lower, so only 40 gigaflops. Across our entire user base, the number of daily flops required is a much more pronounceable 576 exaflops. And that means the number of GPU hours required is actually within the realm of possibility. We only need 18,400 GPU hours, which could be done with a large GPU cluster maybe. And at the cost of 45 cents per GPU hour, this only costs $8,280 now. So we're down from $250,000 a day to just less than 10,000, which is still quite a lot and almost 10 times our budget. But it's gone from being completely inviable to maybe we could kind of do this. But let's keep going. What else can we do to make this cheaper and find a solution that optimizes for all of our constraints? Well, let's take a look at the number of floating point operations per frame that we're running here. We've got this PyTorch model that we pulled off the internet. It works, but can we make it faster? Can we make it smaller? And this is where I'm going to, I know this is NormConf, we're not talking about papers, but I'm going to show a paper on the screen. I'm so sorry. 1 second here. It'll be only up for a second, don't worry. So this is a paper from Google from 2017. It's called MobileNet, and it presents a class of efficient models called MobileNets for mobile and embedded vision applications. Now, what these researchers have found is they can change the model architecture they use for object detection and spend 1/10 of the computing power for only a small drop in accuracy of a couple percentage points. If we use this architecture or any similar cheap architecture to run our model, we can potentially get huge gains in cost or huge savings in cost without significantly affecting our performance. So let's do that. Let's say that we've retrained our model. We still have video coming in here, but let's retrain this model with a more efficient architecture. Now, let's deploy this with something a little more optimized for cost. Let's maybe use TensorFlow Lite, and let's deploy this as a mobile net on our backends here. And each frame of video is still giving us the same outputs, but we only need to spend 4 billion flops per frame instead of 40 billion. That reduces our per stream compute to 4 gigaflops per second, which is much more manageable. Again, down by a factor of 10. Our daily flops required is 57.6 exaflops, much better. GPU hours is now only 1,840. And that means our total daily cost is $828, which again, still a lot, still almost 10 times our cost budget, but we're getting really close here. Our viability is, within a stone's throw from what we've got now. But what can we do next? What's the next thing we can turn to? Well, I see one number in this list that's a little bit suspect, and that's the number of floating point operations that a single GPU can do. This number seems low to me because GPUs get more powerful every single year. And if we were to simply upgrade to more expensive, more modern GPUs, we might be able to get much more performance per dollar here. So let's try that. For attempt number 4, let's use more cost-effective GPUs. And if I pick the most advanced GPU on the shelf right now, I can get 312 teraflops per second instead of 8.7 per GPU. And that means we only need 52 hours of GPU time per day instead of those thousands we had before, even though these GPUs are more expensive at $2.93 each rather than what they were before. And this reduces our cost even more. This means our total daily compute cost for all this GPU time is only $152, which is great. This is amazing. This is only 52% over budget, which for many engineering projects would be a slam dunk, a huge success. But we can go even cheaper. What do we do to get down from $152 to almost $0? Well, I have a proposal here. What if we take this model we have here and we were to make an even cheaper model, even faster model that is way, way, way less accurate? I know we have accuracy bounds. We want a certain amount of precision and recall here. But what if we retrain this model, use some transfer learning and build our own copy of it that is wrong a lot of the time? We can get our per stream compute numbers down here by a huge factor if we just pre-filter some of our data and only deploy our more expensive model on frames that we're reasonably certain already contain coffee cups. So let's do that. For attempt number 5 here, let's use a 2-stage model architecture. So let's take our original model, let's retrain it so that it gives us a huge amount of recall. It catches almost all the coffee cups that do show up in frame, but it's not very precise. Sometimes it'll think that a cell phone is a coffee cup rather than an actual coffee cup or a cell phone. But this model here is much cheaper. It only requires 100 megaflops per second, and it could even run on CPUs, which is great. So we're almost done here. Let's take this and drop this into temporary storage. So the outputs of this model go in there, and then we run a batch pipeline and then drop the results into MobileNet. And then there we have our full precision output. If I race through all these numbers here, because I know I'm almost out of time, this reduces our cost all the way down. We only need to run our heavy model on 0.0001 frames per second. Our offline computing power is in the kiloflops instead of the teraflops. And multiplying all the numbers out, we get to $0.01 or 1 cent. Of course, I'm ignoring a bunch of overhead here, but we're pretty much good to go. And that's all I've got. We talked about 5 things: how to do the simplest approach first, how to process less data, how to make our model smaller, how to use more efficient hardware, and then finally, how to split up our model and use cheap ML to pre-filter our data before applying the heavy ML. And thanks so much for listening. I'll stick around for questions, but that's my talk. Thanks, NormConf.